Welcome to the FOSA webinar series, and thank you for joining us today. I'm Mike Hines, Executive Director of the Fiber Optic Sensing Association, more commonly known as FOSA. Today we have a FOSA hosted and delivered webinar entitled Distributed Fiber Optic Sensing Technology for Electric Power Applications. So we'll be bringing the audience new material as fiber optic sensing impacts new markets and applications. Presenting on behalf of FOSA and its members today are John Beckman, Director of Business Operations for Viavi and FOSA's current Vice Chairman, Paul Baird, Technical Market Manager for Prysmian. Paul and Prysmian have been with FOSA since our earliest days, bringing a wealth of knowledge for this webinar. And finally, we've got Dane Langen, Global Segment Lead in Security and Safety with Luna Innovations. Luna, through their brand OptiSense, and Leos were also founding members of FOSA. And Dane is a DAS subject matter expert, and he's been very active as a volunteer helping FOSA raise awareness of the technology at numerous events this year and last. So many thanks to you all for preparing great materials for today's webinar, and thanks also to the FOSA members who contributed content. With that, we hope that you enjoy the webinar, and we'll turn it over to John Beckman.
Thanks, Mike. Okay, so today we're going to talk about a little bit about FOSA, who we are and what we do, just briefly, and then give a brief overview of distributed fiber optic sensing technology, how it works, and talk about some key applications and use cases. And hopefully we're going to spend most of our time talking about real-world practical applications for the electrical power utility industry, including some real examples of distributed fiber optic sense in work in the real world for electric power grid operators. And hopefully leave some time at the end for Q&A. So first, what is FOSA? FOSA is a nonprofit association formed in 2017. And the mission of FOSA is to raise awareness and drive adoption of distributed fiber optic sensing technology across all the industry verticals you see to the right of the screen here, pipeline, structural health monitoring, oil and gas well monitoring, and of course, power utility applications as well, which is what we're here to talk about today. How do we do this? The example of webinars like the one we're doing today. We also engage in public policy and advocacy on Capitol Hill. We're engaged with standard bodies and speak at a number of industry industry conferences throughout the year. From a membership perspective, the membership is open globally, not just to manufacturers of distributed fiber optic sensing technology, but really anyone who has a play in the fiber optic ecosystem, including Corning, conduit providers like Duraline, Ditch Witch is another example. Also, leading R&D facilities and academic institutions like the University of California, Berkeley, and TU Graz University in Austria are doing some really exciting work in the field of fiber optic sensing, and also actual end users such as Indian Oil, a utility, and Underline, a telecom provider and end user of the technology. So if there's one thing to take away here from who are FOSA and what do we do, just hopefully you view us as a neutral source of information for all things distributed fiber optic sensing. Okay, so what is distributed fiber optic sensing? Anytime we use a fiber optic cable for communication purposes, we're transmitting light down that cable, and some of the light is reflected back to the source in the form of backscatter. And it's by analyzing that backscatter on the fiber that we can detect conditions along the length of the fiber, whether it's temperature, strain on the fiber, or vibrations or acoustic signals along the fiber. The technology behind distributed fiber optic sensing has advanced a great deal in the last 10 to 15 years with increases in compute power, artificial intelligence, and machine learning. It's really improved the accuracy and reach of the technology, as well as its ability to discern specifically what may be occurring and distinguish between, say, routine events like traffic versus construction machinery digging in the vicinity of the linear asset. So, and finally, This technology can be integrated with operators' monitoring and alarm systems and geographic or information systems to provide accurate, hopefully proactive intelligence for proactive prevention of damage before it occurs, and certainly rapid and effective response in the event that there is damage or problems along the linear asset, whether it's a high voltage transmission line or a pipeline or and so forth. Just a bit here, it may be intuitive, but it's a really important concept. With discrete sensing, whether you have cameras, heat sensors, motion sensors along a linear asset like a high voltage line or pipeline, each one of those sensors typically needs to get power, and then there needs to be some method for backhauling information from the sensor for analysis. Unlike discrete sensing, distributed sensing uses the fiber optic sensing cable and provides measurements along the entire length of the fiber optic cable with only power required at the interrogator box at the end, and effectively making the entire fiber optic cable the sensor itself. So how does it work? The intent here is not to go into the deep technical details of the technology, but it's important to understand a few basic terminologies that you may hear when you're talking when distributed fiber optic sensing is being discussed, and how they apply to the various applications we'll be talking about today. So Raman distributed temperature sensing uses the anti-Stokes peak at 1445 nanometers and compares it to the Stokes peak here at 1655. The Stokes peak is temperature independent. The anti-Stokes peak is temperature dependent. So by comparing those two, we can make an accurate measurement of temperature along the fiber optic line. So that's Raman. Bruin analysis of the backscatter uses the two peaks just above and below the 1550 nanometer central wavelength there, and we're looking at the frequency shift of the backscatter to make precise calculations of strain and temperature along the length of the fiber. You may hear this technology also be referred to as a BOTDR. And finally, Rayleigh backscatter analysis works that anytime there's vibration or sound signals, or basically acoustic signals or sound waves in the vicinity of the fiber optic cable, this creates a change in the refractive index of the cable itself, which can be analyzed in the backscatter. And this is acoustic sensing. So the key takeaway here is if you hear Rayleigh or coherent OTDR, think distributed acoustic sensing. If you hear Bruin or BOTDR, think temperature and strain, or DTS, DTSS. And if you hear Raman or Stokes, it's distributed temperature sensing. Putting it all together here, again, we have an example of the output of a distributed acoustic sensing system showing waterfall displays here in real time of events that are taking place along the length of the fiber optic cable. And this is what the operator of the sensing system would see as the kind of raw output of the system. And then applying computation and some intelligence through machine learning, these signals can be interpreted to, in this example, the presence of construction machinery digging, and then fed into an operator's GIS and monitoring system to provide an actual geographical location and an indication of what's going on at that location. All right, I'll turn it over to Paul here for the next few slides. Paul Baird.
Paul, you may be on mute.
You know, I was on mute and talking halfway through this slide, so here we are. Yeah, so the multiple optical cables can be used. Any type of optical cable can be used, but the interesting thing about communications is that the goal is to isolate the fibers from the environment, whereas for sensing, the goal is to have the fiber be as impacted by the environment as possible. So there's two different competing scenarios here. So this particular cable kind of optimizes both. It contains loose buffer tubes that isolate the fibers. That's ideal for distributed temperature sensing with Raman capabilities, and then then those fibers can be used for communications as well. Now the type buffer fiber is used. It's really isolates the fiber, or it includes the fiber directly to the environment of the cable that the cable experiences, and so you can do BRE1 sensing and an acoustic sensing with the type buffer fibers inside. So this is just an example of a cable that's been optimized for use with multiple sensing applications all under the same cable sheath. Next slide. Can do the next slide. Yeah, okay. So there's a lot of investment going on in the utility space, and that's what we're going to proceed talking about. There's the infrastructure bill, which contained a fair amount of funding just for utility investment. There's a great deal of discussion about the quality of the power grid in North America and in other parts of the world, and what is needed for the growth of the power requirements throughout the country. One of the more interesting things that comes up more recently, if you do some studies on or research on how much power is consumed by artificial intelligence data centers, you'll be shocked by the amount of power that's required. And so we have nowhere near the grid nor generation capacity capabilities for supporting the sustained growth of artificial intelligence data centers. So it's a huge opportunity for investment in power grid infrastructure, and it's ideal to take an aggressive view to include optical sensing in those new investments. Next slide. I think that's back to you,
Great,
John.
thank you. Yeah, great, thank you, Paul and John. So let's talk a little bit specific about acoustic sensing. So you heard John mention a coherent OTDR. If you're familiar with what that piece of technology is, it's a sensing tool, or if you're not familiar, it's a sensing tool that basically looks for attenuation on fiber cables. So internet providers and telcos and anybody with a network want good network uptime. So that's important. What we've developed and what the industry has developed essentially through partnerships with militaries, it's an event-based system, so it's a coherent or a dynamic OTDR. So we're not only sending the light pulse, but we're seeing the backscatter as it comes back. As John also mentioned, the gauge length of the light pulse that we're firing down this fiber optic cable will give us an indication of where we see some backscatter points. So that gives us these distributed segments or zones along the fiber optic cable. This is really beneficial in any event-based application. So this is conducive for security applications where you need to be monitoring for intrusions. This is conducive for any kind of event-based infrastructure monitoring. So for leaks along pipelines, faults along power cables, any type of event or damage. There's multiple applications for DAS outside of electric utilities too. We won't go into that right now. But essentially what you're doing is that the vibrations hit the fiber cable, the strand that's interrogated, that's lit up with the laser lights inside that cable. There's a tiny amount of stretching that occurs or strain on the cable, and that changes the insides of that fiber strand that's interrogated, and light bounces back differently. And so that's really what we're doing, is we're interpreting the bounce back. If anybody here, so I'm a musician, and that's my original, my first career. And this makes sense to me because I understand sound vibrations, right? So there's intelligence behind sound vibrations. There's patterns associated with it. There's intensity. And there's other variables that are even kind of hard to describe when we're listening or feeling music. And I did say feeling, so you can think about that. Well, that's really what we're doing. Our brain's doing the same thing as these instruments do. And I've got a couple videos here to show that in real world. And I'll let John switch to the video. What you're going to see is a software and a camera view. And we're going to simulate some digging here. And I think the video's pulling up on another screen. Yeah. There we go. Okay. So, and John, I think, is this on a loop? I can't remember if I asked that.
Yes.
Okay, cool. When this plays, so you see the excavator over on the right-hand side, you start to see those bucket impacts, or the shovel impacts. After a certain number of those, you can get an alarm. And so that alarm actually says mechanical digging, because we understand what a excavator looks like. There's a tonal to the engine, for instance, of the sound from the combustion engine. There's the shovel strikes on the ground, and you know, the basics this is a system that's on your right of way, or this is a system that's on near your asset. So if there's work that should be going on, this shouldn't be an issue. But if there's unauthorized work, and we'll talk about that a little bit later, you can get those alarms to it. You can go to the next video, John. And we talked, I mentioned event-based. You know, these, I like these scenarios here because it's very straightforward. So you can actually hear and see the impacts of that lid right there on the right-hand side in the raw acoustic data. That's again interpreted by the software, and then we've just set up an activity alarm for that location. The second activity here is the manipulation of cable, or you know, whatever's in that vault, and then you can actually see that pull. You can see him grab the lid, and its impact whenever it closes again. So that's an intrusion. If that works unauthorized, or there's multiple owners in this right of way or in the common duct bank, then you can understand what may have happened, even forensically, if there's been a fiber cut or a fiber break. You can go on to the next slide. So we'll start to talk about this. Fiber sensing can mean multiple things for a single user or a single customer. Event-based, so these are security-driven or safety-driven. So you can be worrying about your own people, or you can be worrying about people trying to get into your facilities. You can understand certain things about patterns of life. These are some hot topics that we've seen from the power utility segment. So a personnel approach could be that, you know, this is a liability issue. Has a kid's ball, you know, bounced in over a fence into a distribution yard, or, you know, what's actually happening. You see on the news, there are still, and you still see them, people shooting out substations and planning attacks. So we can actually get information prior to that event going on. I'll describe that in the next slide. But then you can monitor infrastructure, so you can do some different things with temperature and strain sensing, but you can also do some things with acoustic sensing, and then all the way to the aerials and the underground transmission line. You're gonna hit the next slide, John. So back in 2013, there was a major incident in the western part of the United States where a substation was a coordinated attack on a substation. This actually caused NERC to revise some of the critical infrastructure protection standards. There was a system installed. This data is from a system installed monitoring a rail line. So this is actually developmental work that was done in partnerships with some research groups and near the area. And coincidentally, and this is purely coincidentally, we saw these activities. So when we went back and looked, the industry looked at these different elements of the raw data, we started to see this is vehicle traffic moving. This is the length of the cable here on the bottom, and this is time. Colors show intensity. You can see here after the fiber was cut, there's no more signal after 12:58 a.m. So you see all these precursor type activities, and then you certainly can see the event and then the cut. So what happened after they occurred is the bad guys shot out a bunch of transformers at the substation, and then those transformers systems were not allowed to communicate back to controls that they were beginning to overheat. So it caused some major issues. You can move on to the next one.
Okay, thanks, Dane. Distributed temperature sensing, as we talked about earlier, provides the capability to accurately measure temperature along the entire length of the fiber optic cable. And the useful application here is the proximity of the cable to, for example, a high voltage electric transmission line. Having the fiber optic, by measuring the backscatter of the light and making precise temperature measurements along the entire length of the fiber, it enables operators to detect hotspots, to drive alarms off temperature variations and kick off other response systems such as cooling. And then the capability to accurately measure temperature here can also be used to feed other systems to operate the transmission line and the grid more efficiently overall, by getting the maximum potential out of the transmission line, and as well as making sure that as well as enabling a longer life of the facility as well. So how does a practical example of how distributed temperature sensing works is that we are measuring, again, the temperature over a length of cable. In this example here, it's actually the picture in the lower left. We're measuring the temperature along a buried fiber optic cable. And you can see the temperature represented by the gray trace here is at 4:23 a.m. The blue is at 8:23 in the evening, and the orange at 2:23 in the afternoon during the hottest part of the day. And you can see the temperatures are fairly similar throughout the buried length of the cable, but where it's exposed here, we see the variation of the temperature from basically early in the morning after being in the dark all night and relatively cool, to the hottest in the afternoon, and in between here in the evening. And the trace here at the bottom is the raw output from the DTSS analysis, so the BOTDR. And then this is the graphical representation showing the variation of time with distance to provide actionable information to the operator, in this case, that they've got a piece of cable that's become exposed due to erosion. So just a practical example there. I'll talk briefly here about real-time thermal rating, or dynamic line rating. And really, it's a computational engine or methodology that's standards-based by IEC standards 60287 and 60853. So it's a standard-based methodology for operating transmission lines to maximum efficiency, and also when applied over time can lengthen the lifespan of the asset as well. And its key point here is that distributed fiber optic sensing, or distributed temperature sensing, does not provide the real-time thermal rating, but it's one of the key inputs. Again, the ability to accurately measure temperature at at small spatial resolution across the entire length of the asset is an enabler to real-time thermal rating, or dynamic line rating. As Paul said earlier, as we're looking to get more and more out of the grid, when the grid or the transmission system becomes congested, it decreases efficiency on the grid, increases costs to the operator, and by default to the consumer. And additionally, in coupling renewables into the grid, as far as additional sources of energy and going green, there's kind of a constant need to improve the efficiency of the electric distribution or the transmission and distribution system. And real-time thermal rating and dynamic lining rating will play a big part in that going forward. And it's just the key point here is that distributed temperature sensing is one of the tools in the toolbox to help enable that going forward. All right, and I'll turn this back over to Paul.
Yep. So one 100% use case of optical sensing for power grid transmission is offshore wind farms. Essentially every cable that goes into the subsea floor connecting wind farms to the shore contains optical sensing. That's 100% of the time, just because the use case has really proven that that's extremely valuable to do this investment in the optical sensing system. Here is a description of a project that Prysmian did a few years ago off the coast of Britain. It's called the Hornsea 1 project, and we we have 3 different systems in parallel, and you can see kind of the details of the length, but potentially we're 120 kilometers off the UK coast to begin with this, to connect into the wind turbines. Next slide. I think there's the full distance of coverage is the longest length in instrumentation. I think there's another visual yeah, there we go. Okay, this gives you a sense of what it's like in the on land portion, then the undersea portion, and then the connection to the substation or the generations windmills out there themselves. And your operating attenuation is 0.25 dB per kilometer during the design phase, and that's what you're trying to estimate your budget around. So this just gives another example of this showing here. Next slide. Okay. What happens is there's a halfway through the route from the wind farm to the onshore is what's called a landing point that was a platform where equipment is installed and so forth. So the cable comes out of the ocean and attaches to the platform where there's some monitoring done, and that's where some of the sections are. And you can just see the change in temperature of what goes on when you come out of the ocean and then go back into the ocean. So that just is more data showing the example of what we're doing with this 120 kilometer route from off the coast of Great Britain. Next slide. So the key point of this is that you are monitoring the actual temperature of the conductor itself, and you can just you're able to identify that. In the air section, as it points out, you can see the largest variation, and the land segment has the smoothest section because that's where the cable is buried. Again, another example of the Hornsea application, but the key point of this whole discussion is that for offshore wind farm applications, 100% of all of those applications have optical sensing, and it's incumbent on operators to start thinking about how to deploy the same technology in land-based systems as well, to take advantage of the transmission capabilities that monitoring conductor temperature allows you to do. Next slide. I think this is you, John.
Back over to Dane.
I think I'll take it. Yeah,
Okay.
yeah. Thanks, Paul. Yeah. So here's another application for distributed temperature sensing. So let me explain real quick, what is linear heat detection? So there is a conventional linear heat detection technology where it's a metallic cable, and essentially the cable melts. That's how the alarm is triggered. The cable fails. This is not that, and it's kind of a little bit of a paradigm shift in specifically that nomenclature, linear heat detection. What distributed fiber optic sensing provides in the linear heat detection mode is, because it's in distributed nature, you get continuous temperature monitoring along the whole length of that fiber cable. That's a big one. There are no physical zones that you have to engineer. So physically, you don't have to set up a zone. It's all set up in the software, virtually. It's flexible. So if you can see in the middle of this slide, you essentially have three parameter outputs. You can get minimum and maximum temperature, rate of rise, and then you can get the temperature delta. You can architect a true Class A loop cable routing in case the cable is cut, so you can have some failover there. You reduce false alarms, and then you get precise and accurate actuation of fire suppression systems. Excuse me. So really what that means is, this is a distributed sensing system. The fiber is running on beams in the ceiling. It can be touching batteries. I'll show you in a slide in a second. It can be on tanks. It can be in tunnels. It can be in your duct bank and vaults. This could be anywhere. The fiber is feeling the temperature. Every part of the fiber is feeling it at all times, much like a nerve ending. Not unlike the distributed acoustic sensing system. You can move on to the next slide. So you can, the distributed nature allows you to set off sprinklers, for instance, in specific zones. So here is an example. So this is in a battery storage facility. So it's simple as, or this one first. So in monitoring batteries, the news these days, you start to see more and more reports of runaway lithium-ion battery fires as we move to a more electrified world here. Electric vehicles are going to have charging stations. These could be put in facilities, and then in the storage facilities for the power utility segment, monitoring these batteries for hot spots, potential damage, or fire. Next slide, please. So the sensing cable can be laid on or tied to these roof panels, and then batteries are stored, and then you get indication of a specific hotspot, right? So it's less ambiguous. Next slide, please. So as we're getting close to the end here, what we've discussed in power utility segment is there are multiple applications fiber sensing can provide. The fiber infrastructure is either there because it's part of an already established communications infrastructure, or it's purposefully designed. Placement of the cable next to the asset you want to monitor, for instance. And then you can pull out multiple applications. So you train users on what to interpret, or we're getting automated alarms with actionable information from the systems for you to move cameras to a security incident, for instance, or you've got a section of the grid that needs to be monitored because of some continuous work that's going on. You might turn on some awareness at a specific scheduled time. You can combine all those into a single application, so that's a single fiber-based application. Those outputs can be interpreted and then sent into the customer's control centers. And then you can take it even further and then think about, layering this in a platform. You have an initial detection system that the customer has confidence in because it's going to be telling them specific things, and you've walked through those scenarios with them based off of threat profiles around facilities or along right-of-ways. And then those sensors are combined with other types of sensor systems, could be cameras, thermal imaging, could be point sensors, anything en route. And then customer ties that all together into a single ecosystem with a system sensor aggregator, and then operators have better intelligence to make better decisions faster. And the last little topic I'll bring up here is, you can move to the last slide there, John. So I just noticed my number 2 is off the image here, but I'll explain it. So all of this technology coming together, we've talked about different applications, different cool things that this can do. This sums it up pretty simply, and this is a huge value. So if you've got one of these systems installed, for instance, at number 1, there's some activity at a location, right? So we get the location of the activity, and we're going to get some information about what's going on. That system or the technology then alarms on the system, and that's sent to the one call. We worked, the industry's working on integrations to these one call groups. This is one of the ones that has been successful in Texas. The one call center then cross-references against any open active tickets. And you can see you've got an active one call ticket in this spot, but actually the digging alarm occurred at another location. So that alerts Texas 811 to notify the operator, and then the operator responds accordingly. This streamlines that whole process. So not only do you know about unauthorized activities, but you can understand authorized activities and any other general security things that are going on, especially if there's work going on and there's yards and so on and so forth. So this is pretty simple. I think it's elegant. System alarms, cross-reference active open tickets, and then you can come back and respond appropriately. So thank you very much. You can move to the next slide, John.
Okay, thank you, Dane, Paul, and John, for a great presentation. We do have some questions from the audience, so I'll kind of step through these. We've got a few minutes left, so this is very good timing. First question, I guess maybe I'll toss this over to John, can temperature, strain, and acoustics all be measured at the same time on the same or separate fibers? A related question was, are dedicated fiber strands required for sensing purposes? Maybe you can weigh in on that.
Thanks, Mike. Yeah. So and Dane and Paul, feel free to keep me honest here. But I think in general, as we said at the outset, some technologies like Bruin, BOTDRs, you have the capability for measuring both temperature and strain, and that's on one piece of fiber. It could be a purposefully installed fiber for a specific application, or it could be using a dark fiber on an existing network. Typically, if we talk about combining acoustic sensing with strain or temperature sensing, it's two separate fibers, or you're using the same fiber for either technology alternately and not simultaneously on the same fiber. But I think from an application standpoint, it's also in some applications, like we talked about, measuring temperature along for instance, a high voltage conductor. You want to, if you're doing temperature sensing, you really want that fiber located as close to the cable, if not within the sheath itself, to get the best temperature reading that you can, the most accurate temperature. Conversely, if you're monitoring that same cable using distributed acoustic sensing for proactive damage prevention, like Dane just talked about, you probably want that cable just outside the sheath so that the sheath isn't serving to attenuate some of the vibrations, and you get more precise and more sensitive acoustic measurements. So it's important not only to take into consideration of what the technology can do on one fiber or multiple fibers, but really think about the application and selecting the fiber and the location of the fiber for that application.
Yeah, thanks, John. Here's another good question. This is more of an application question. Can distributed sensing technology be used to detect and identify the source location of partial discharge? think, I'm not sure to toss that one over to. I know some of FOSA members like Sensonic and AP Sensing have published on this, but Dane, maybe you've got some experience with partial discharge applications?
Yeah, from the acoustics perspective, it's a challenge. There's different, you're thinking about different frequencies that you're going to be paying attention to, and those are very high frequencies. When the systems are, when you're talking about this in an aerial application, there's a lot of high frequency information in the air, obviously. So that's part of it. We have done some work in that area. It's a possible. It's a novel and a new solution. I think we're all still chasing a gold standard for. I'll let Paul or John comment too.
I think that was well said.
Yeah, that's fine. So we actually have quite a few questions. I'll keep kind of pushing through here. Here's one. Are the detection algorithms open source, or are they vendor-specific software features?
I'll jump in real quick. I think there's you can do both. Personally, we have customers that use ours and that develop their own. So you can use these as instruments, or you can use these as a total solution.
Great, thanks for that. This next question is related to some of the commentary that John made a minute ago, but I'll see if I can paraphrase the question. So how much does it matter where the optical fiber sensor is placed relative to a power conductor? And are there placement preferences between applications of temperature, strain, and vibration? Maybe the easiest way to answer this is to take temperature, strain, and vibration independently and talk about positioning of the sensing cable.
Yeah, and like I said earlier, there are some custom cables and some cable manufacturers that actually, manufacture high voltage transmission cable with embedded fiber optic lines in the cable itself. And I think the primary application there, with that fiber embedded, as we said earlier, is temperature and strain monitoring.
Yeah, I agree. That's what the submarine cables we taught that Prysmian makes. The optical fiber is embedded in the submarine cable itself, and then in the other applications, Prysmian also embeds optical fiber into power conductor cables for various transmission applications. We have a couple of utilities that are starting to do land-based systems experimentation with this. So that's one solution. Another solution is to place the optical cable next to the power conductor, and you get into the same discussion you get into with pipeline operators when they place an optical cable near a pipeline. You're trying to get the cable as close as you can to the cable, and so 18 inches is really kind of a number that I hear kicked around. It can vary depending upon acoustic sensing. Is if you're doing temperature sensing, the closer you are to the asset, the better. But if you're doing acoustic sensing, you're really sensing the environment around where the asset is, so it could be a little bit farther away. So it comes down to the application that you're trying to accomplish with the optical cable relative to the asset you're monitoring. But closer is better, but it isn't always possible. But the distance is really within a meter or so, and others can comment on that.
Yeah, thanks, Paul. That's very helpful. Here's another question. So what is the range or distance of a sensing system? And by that I mean one interrogator unit connected to an optical fiber sensing cable. What's the distance you can measure or the span that you can measure for vibration, for temperature, and for strain?
I'll start off and talk about DTS. I mean, typical, like what you see advertised in the industry, and it can vary 10 to 100 kilometers with a spatial resolution of about 1 to 5 meters. and a sampling time of 2 to 30 minutes, and an accuracy of anywhere from 0.5 degrees to 5.5 degrees. And the reason I'm giving ranges there is really because to some extent it's what the system is being optimized for, and there are always trade-offs. If you want to go longer distance, then perhaps when you're choosing to optimize the measurement for a distance and selecting a pulse width for to use, you're making trade-offs maybe between accuracy for a greater distance or a higher accuracy over a shorter distance, and so forth. So that's generally for DTS. Dane, do you want to take acoustic sensing?
Yes, similar for acoustic sensing, limitations based off of the application basically. So if it's a long, super long run, we're talking 70, 80, 90, 100 kilometers, for instance, there may be just awareness for third-party intrusion or accidental damage, like we've been discussing here, versus pipeline leak detection, which requires a little bit more of a refined way the system looks at the applicate or the asset. So it's exactly the same. The longer the cables, these cables that ultra long cables that are getting built, there's solutions being designed today to get that out there, and kind of thinking subsea and in that scenario.
Great. Thanks, Dane and John. Here's another question. Are there applications currently or in development applying distributed fiber optic sensing to overhead cables? So in today's presentation, we discussed quite a bit around submarine and buried cables. Are there applications in overhead cables as well?
So one of the, I think, challenges is that there's a great deal of overhead transmission cable deployed out there that does not have fiber optic cable, either fiber optics for sensing, either embedded in the cable or on its exterior. I know there are a number of manufacturers and I was at the Edison Electric Institute's transmission and distribution forum in Houston this spring, where there was a presentation of a number of transmission cable vendors are now putting the fiber optic cable within the newer transmission lines for new projects that will enable that for overhead lines. I'm sorry, Dane or Paul, you're going to add to that?
I was going to say what you just finished with, as the advent of hybrid or cables with fiber embedded in it. Yes, there's certainly a lot of applications that can be utilized. If you're talking about sensing from the OPGW, that's again, it's got its inherent challenges. How far away is it from the conductors? What exactly are you trying to pay attention to? So again, the industry's trying to solve that, and we feel like there's some development with new cable construction.
Great. Thanks, Dane. Here's another one, I think probably best for you, Dane, because I know that Luna has had some activities in the rail space. Can use of distributed fiber optic sensing, and I'm thinking DTS, be used to monitor the actual rail temperature itself in railway applications? So you're looking for, heating and cooling of the steel rails, probably trying to avoid buckling and so forth. Is there a use case for that or something in the works?
That's actually the first time I've ever been asked that specific question. So I'm having to think a little bit. You certainly would see expansion. The principle is you're paying attention to the cable, right? So it's near the asset. So if you're paying attention to a rail line, the fiber is usually off to the side. And so, but I guess what you can do, so you can monitor ground movement, and that's certainly an application that out of the box, rock fall, landslide type, things that go on in those parts where that part of the rail line runs through mountainous regions, or where there's a lot of weather or rain, or erosion could be occurring, around bridges. So you can monitor that. You'd have to get close to the rail line. I'd almost feel like you could get a really good signal about what's happening with the rail line from an acoustic sensing system versus a DTS system. But if you put the fiber close enough to that rail line, or you could somehow engineer it that it was being monitored directly on the rail line, I can see that happening too.
Yeah, I can envision, when there's no rail traffic and the rail is just kind of in the background, vibration could be emanating from rails that are expanding and contracting. There's another, maybe another approach that may or may not have been developed. If you designed or engineered a system similar to what Paul Baird described in his cable description, where you had, one fiber that was intimately coupled to the cable and its jackets, and a second fiber that was in a loose configuration, you could clip or attach that cable to the base of the rail somehow along its length, and then you'd be able to detect both temperature changes directly from the rail in concept, and potentially transduce strain changes of the rail itself onto the coupled fiber. So that might be a way to try to experiment with that. But I'd say it sounds like a promising application. There may be examples of experimentation that have happened in the market that I'm not aware of, but that's the approach that I would consider using.
Yeah, if whoever asked that question wants to follow up direct, we can figure out with one of us.
Yeah, we'll be able to make email connections and such after the event's over. Here's another one. Maybe this is a good one for you, Dane. Are there examples of platform ecosystems where fiber optic sensing is a crucial layer in the architecture?
Can you repeat the question?
Yeah. Are there examples of platform ecosystems where the fiber optic sensing piece is a crucial element or a crucial layer in the architecture?
Okay, yeah. So first one that comes to mind outside of the power utility space comes to mind is, borders. So in an ecosystem, and this is big, so big kind of macro scale, right? In an ecosystem, you've got the tip of the spear. So this is what you're going to be actioning on, right? So you're going to have the tip of the spear from the sensing element. For instance, along a border could be the fiber sensing system that's buried. And so that's going to be instrumental in making decisions on how to respond. So you're going to respond with force, or you're going to respond with less force, depending on what you understand about the threat. In a sensing environment, more operationally, you could have multiple types of leak detection technology. So you could have software-based computational flow. It's measuring, taking flow measurements. You can have specific point sensors, flow, and point pressure sensors taking readings along specific points along the pipeline. Valves are going to have monitors. You can have facilities that are en route. Compression stations have their own sensing systems. And then all that feeds into SCADA, basically. So it's telling the SCADA room operator everything that's going on at the same time. And then kind of another one, and this is in the security space, this is starting to happen, where we feel like it's a reliable approach, where you have one piece of technology doing its analytics to refine classification on a target, and then it will tell another piece of technology, hey, this is what I think I see. Do you see it too? And all this happens so fast before a human even gets involved. And that's very conducive for fiber, because fiber's covert. It can be buried, it can be in conduit, it can be just next to the road. And you can very easily get coordinates and location coordinates from this technology. So you can move an optical device, for instance. So if you've got a really refined fiber sensing system that can tell you, hey, at a perimeter gate, this is a person walking towards the perimeter gate. And then you can move a camera on it. And then that camera system And the video management software can have an analytic package that paints zones and then starts looking for a human. So there you have two pieces of technology trying to agree on something before a human gets involved, increases probability detection and reduces all the false nuisance alarm rates that we all have to fight.
Yeah, that's great input. And it kind of leads me to another question that popped up, which is, can you explain a little bit more about the alert integration or alarm interface with customer systems like SCADA or CCTV? In other words, how do these DFOS systems integrate with other parallel systems?
So the system can trigger serial outputs, right? So you can actually have on-off. So you can have an on-off for a certain parameter that this fiber sensing tells you. So you could get an intrusion, you could turn on an annunciator, for instance. You could turn on an alarm, you could turn on some lights. And that's kind of at the, the basic end of a spectrum. And if you go all the way to the other side where it's data rich, there's information that's being shared in between, kind of like I just explained, that would be like a HTTP type interface, right? So, and then in the middle there's all different other kinds. And it really just depends on the operators. Well, what it comes down to is the system the operator's using. And then that kind of is backwards even one more step, is what does an actual response look like from that operator? Do they call law enforcement or are they calling maintenance? If they don't have a practice, and this happens, if they have an intrusion, but they don't know if it's a good guy in the wrong place at the wrong time, or if it's a bad guy, right? And they just send maintenance, well, you're putting your people in danger. So, if that makes, so you get some better information the more you get to the rich side of the spectrum there. But for instance, in the power utility space and the operational side, SCADA controls, Modbus type interfacing, OPCs, pretty standard in the market. I'll let some of my colleagues jump in. Sorry about that.
Yeah, so I'll interject as well. The one example that I shared with the submarine application is that they're fully integrated. You don't make the investment in the transmission capacity or the generation capacity without the optical sensing to go along with it. So it's fully integrated to monitor the health of the transmission cable as it lays on the seabed. And so that's the most common example of 100% utilization where it's fully integrated with the application, and no investments are done without it.
Yeah, that's great input and a good example, Paul. Thanks for that. So looking at the clock, I guess we'll start to wrap things up here. So thank you to Paul, Dane, and John, and all FOSA members who had a hand in creating this presentation. Really interesting stuff. For those in the audience, FOSA greatly appreciates your interest and attention, and we hope that you join us for future webinars. Today's webinar has been recorded, and it'll be available typically within about 24 hours on FOSA's YouTube channel. So please subscribe to that channel, follow us on LinkedIn, and feel free to send us notes and emails and such, and we'll try to get back to you with responses. And with that, we'll close today's webinar. Thanks, everybody.